very young children, age 3 to 5, produce a different test outcome than older children. So the test basically tests developmental stages by checking if the children take only weights into account, that would be stage 1, or if they take the product of weight and distance into account, which is the right thing to do, or if they just take distance into account. So such a test is then used, if it's considered valid, to infer positions of children in these discrete stages of development. If we now apply this to machine learning, what do we get then? In multi-class classification, a variation in the attribute would mean that we vary a test example. So features and labels are varied. A measurement outcome is a model prediction. And the aforementioned causal relation would mean that the variation in feature values and labels has to correlate invariantly across environments. So what this looks like is we are all there. So if we have a few nice random or standard or biased test splits, trained test splits, then we can basically do our standard evaluation, and in the end what we will get is is a validity test. But there is more to validity. What is more to validity is sorry. What is more to validity in addition to what we see here is circularity. And this is one aspect of validity I want to talk about. It's an aspect of validity that is not normally considered in NLP. So what is a circular feature? A feature can be considered circular for a data set. If there exists a deterministic functional relationship between the feature and label that is known a priori. So what does that mean? If we have such a relation between a feature and a label that is known a priori, then the best model is already known. It's the deterministic function. And even if we apply machine learning, all that will happen is our machine learning model will reconstruct this functional relationship, but nothing else. So the goal is to build a test, a statistical test that checks for circularity. And so the question that we want to answer is, assume we know the functional definition of the target, but not the training data of the machine learning model. So it's a black box model. And the data we have is predictions of the machine learning model. So what we want to do is we want to detect by a statistical test if circular features have been used in the data. So the test looks like as follows. So we have a data set of features and labels. We have a set of candidate circular features, so that are basically all the features that we use in our training, including the features that we know define the target. And then we train models, and the models we are training are generalized additive models, and we do the following test. We test first for deviance. Deviance means we find the model with the maximal likelihood of the data and the smallest degrees of freedom. So basically the model that explains the data best. And we look at the feature shapes of the model. So what we do is we want to make sure that only those features that maximize the deviance have a contribution to the prediction, and all other features are nullified. So let's look at an example. The example that it's a real world example from patent prior art search. So it's part of NLP if you want. It's, and the problem in this scenario is that people are using a deterministic functional definition for the labels. So they use patent citations. So no citations means relevance score 0. And in citation of the inventor, relevance score 1, examiner citation, relevance score 3, 2 family patent means relevance score 3. So if we now train a model, so the example I'm talking about is a nonlinear combination of a neural model and TF-IDF features. And the questions that we ask is, what if patent citations are also included in this model? And this has actually been done by some researchers in the Clay IP shared task. They call it the KISS principle. It's the keep it simple and straightforward principle. So if we have the information about citations, let's include them in the model and improve the results. Of course, what you will get if you do that is not a better model. What you will get is the following. So what we see in the left-hand column here is a model that does not include the citation features. And the model, so we look at the second image in the left column, tells us that TF-IDF is a very good predictor for what we want, a very good predictor of binarized relevance, not relevant to relevant. And the neural score is also a very good predictor. As soon as we include the citation features, what we see in the right column, then we get a deviance of 100% instead of only 70%. And we can model the target function 100% accurately, and all the other features, namely the TF-IDF and the neural features, are gone. They are not, they don't have any contribution anymore. So basically what this model learns is just the citation, reconstruct the citation features. So you might say this is not a surprise, and it's maybe also not a problem in NLP, but I would say, well, this is the only example I found so far. There might be many more examples. Where it is really a problem is in general in data science. So for example, if you look at medical data science, then for example, the so-called SOFA score, which is a very important score to predict sepsis, the disease of sepsis, is defined on measurements of a certain type of, on a certain type of measurements, named a measurement of bilirubin. And if the bilirubin measurements that are normally taken from a patient in the ICU are included in the features of the data set that are used for machine learning, then you can accurately reconstruct the score function, the SOFA score function, which consists of 4 scores. And you will see that in the right column, again, we include the bilirubin measure. On the topmost, right topmost panel, we see that we can reconstruct the target function and all the other features, thrombocytes, HCV, and all other measurements which contribute to the SOFA score. They are all gone. So it's to summarize what I want to say about circularity, since it's not a very familiar topic. Circularity inhibits machine learning at its core. So all you will do is you will learn to reconstruct the known functional definition of the target. So this is something that should be kept in mind, especially if it's not clear how the data are constructed. If the labels are not given naturally, if they are done automatically by a functional definition. And the remedy is not machine learning. The remedy is really, you have to detect those features and remove them. And more circularity problems and more validity tests and are in our book. Okay, so my question to the host, to André, is, should I take questions now or should I just move on and finish my talk? Because I have 2 more sections. So one is on reliability.
I think it's better to move on because we have around 5 minutes into the next talk. So
okay. So reliability is the second topic, and reliability can be simply defined as the consistency of measurement scores across replications under varying conditions. And what we will look at is measurement scores being labels annotated by humans or predicted by models, and the replications under varying conditions is varying raters, varying occasions of ratings, and metaparameters of the models. So the idea is we take well-known statistical techniques that have been used in social sciences before, to achieve this task, namely variance component analysis. So basically what we want is we want to untangle the sources of variation in our measurement. So for data annotation, this would be raters, and for machine learning, it would be metaparameters. And then we define a coefficient, and the coefficient is, dates back to Fisher, who defined it in the 1950s and gave it the name intra-class correlation coefficient, which is, yeah, we don't have to be hanged up on the name. So what it is, the idea is that the ratio of variance between objects of interest, in our case, the objects of interest are the sentences in the test sentence, in the test set. The variance between the test sentences should be always greater than the total variance. So it should be definitely greater than the sum of the variance of objects of interest and the non-substantial variance, which is the variance due to metaparameters or for raters or anything else that includes noise into the measurement. So the basic idea is you want to have a coefficient that tells you, is my measurement under replications, under the different sources of variation reliable? And reliability then means I can distinguish the object of interest and good enough with a ratio that is, as we will see, a good measure, a good number for this ratio is 80%. Okay, so let's look at what is variance component analysis. So I don't think I will have a lot of time. So variance component analysis, just believe me, what we can do is we can take a linear mixed effects model on data that consist of, for example, for machine learning, different outputs of the system under different metaparameter configurations. This is data that everybody has anyway. So everybody does metaparameter search, and you just have to store away this data for the metaparameters, and they are fit by a linear mixed effects model, and the linear mixed effects model has as random effects the interesting effects, for example, the sentences and all the other factors that influence the variance of the measurement. And then we compute the reliability coefficient that is defined in the same way as the ICC before. We have to make sure that the variance of the object of interest is the greatest. So let's look at an example for data annotation. So this measure is supposed to replace measures like Krippendorff's alpha and Cohen's kappa, Scott's pi, and so on. So the linear mixed effects model takes as effects the sentence, the rater, and the instantiation, and all interactions between sentence rater, sentence interaction, rater interaction. And what we will see here for an example experiment where we looked at learning from post edits and learning from error markings, that the raters that did the error markings had a 12% variance on the sentence and a greater variance between the raters themselves. So that's not a good result. And for post edits, it looked a little bit better. 60% of the variance was due to the different sentences, and less variance was due to the raters and the repeated measurements, the repeated annotation, but this is also not a satisfactory result. So what we want to have is something like 80%. So what we can do with these LMEMs, we can extrapolate how many raters and how many instantiations we would need in order to get a reliable measurement. So it, including these raters and instantiations, you can include any other factor that you are interested in. So this is basically following up on Barbara Plank's talk today. She was interested in how to figure out what are the sources of variation. That would be a way of figuring out what are the sources of variation. And if you're interested in combining and filtering, then you would know I get a reliable judgment for post edits, for example, if I take 2 raters and 2 instantiations. For markings, you need more. So what is maybe more interesting to you is reliability of machine learning models. And here you see the model looks like this. We have as our random effects, we have all the meta parameters that the model has: learning rate, random seed, encoder dropout, decoder dropout, and so on and so forth. And we will see, okay, so we did a partial grid search on 27 models. This is the actual experiment that was done in the marking and post-edit paper. And we see it's reliable. At 80% of the variance is different sentences. So the test set was from TED Talks, and we took different talks. So there was a nice variation in the test data. And we see if we look at more models, so an extended grid, then the variance goes even up for the sentences. So the reliability goes even up. So why is that? Because we are including meta-parameter settings that are actually not of interest. Every human modeler knows, no, this I don't want even try to work with a dropout rate of 0. And if you include that, then you get a lot of, you get more variance, and so your coefficient goes up. So, but the thing to do is the actual grid search that you did for your model development. That should be the basis of the reliability testing. Okay, what's even more interesting, what you can also do with these LMEMs, you can look at the interaction of meta-parameters and data. So here what we want to look at is the interaction of meta-parameters and data for a particular setting. Namely, do we choose one rating or another rating for the markings learning? And we want to see, does it have an effect on short sentences between 1 and 14 words, medium-sized sentences, or larger sentences? And what we find is only for the long sentences, there is a difference between this meta-parameter setting. It doesn't make a difference for medium-sized or short sentences. So the long, complicated sentences, it makes a difference if you set one meta-parameter this way or the other way. So that's also a nice way. So you basically, if you have an idea what you're looking for, you can put this in the model, train it on the data, and see, is this effect meaningful? Is it, does it make a difference? Is my model reliable under these interactions of data and meta-parameters? Okay, so to summarize, the main idea is not really the applications of LMEMs, but it's this reliability coefficient that what you do is you make sure that the variance of objects of interest is larger than the variance, the non-substantial variance. And this gives you, for one experiment, allows you to measure reliability. You don't have to do it comparatively. You can do it for your one evaluation experiment and be satisfied, or change the model so that it's more robust to changes in meta-parameters or data. Okay, then the last part, significance. This is just 3 slides, and it basically makes a connection between significance testing and this reliability analysis. And so what I want to do is I want to make a plea to use the generalized likelihood ratio test as your favorite significance test, because the likelihood ratio test can be directly plugged into this LMEM analysis, and in difference to all other significant tests I know of, it's a one-stop approach to significance testing under sources of variation. So what you can do is, for example, you can take models that vary according to, let's say, random seeds, train a few models under different random seeds, train another, the competitor or the baseline model, under different random seeds, and then do a significance test. And so we did that for interactive machine translation, and the setup is a very simple setup. It's called the nested model setup, where you have to make sure that you have one effect that basically distinguishes the baseline model from the model that you're looking at. So here it's a model that is doing fine tuning from a model that is using a baseline. And the nice thing about it is you just compute the likelihood of one model and the likelihood of the other model for all the data that you have collected. And what the likelihood ratio test tells you, you reject the null hypothesis that there is no difference if this statistics yields a value close to 0. So there's more to say about it, but it's a very simple test. It's implemented in most LMEM packages on the side. So the thing about significance testing under variations is if you do LMEMs or other model-based approaches for reliability analysis, then you get for free on the side a significance test that allows you to include variations. And the power of the test will be increased for more reliable models. So to conclude, so what I wanted to tell you, after 10 minutes, finally it worked, how old-fashioned statistics, so old-fashioned in the sense of not neural networks, but statistical models that have properties that are very important for this application, namely identifiability and consistency. So they are convex, the objective functions are convex functions. They have one optimum that you can use. The maximum likelihood estimators are consistent, and then you can interpret the parameters of the model directly. You can be sure any training run will converge to the same models. And this is what I think is a really important property of models if you want to use them to interpret or to do a statistical test for. Thank you very much.
All right, thank you very much, Stefan. Glad that you were able to present everything despite the technical problems. Okay, so I think we don't have time for questions and we need to move on to the next talk, unless there is a very quick question that someone wants to ask. Okay, so I don't see anything in the chat. So let me suggest that in the interest of time, we move on to our keynote lecture.